In this video, we will talk about some prime and composite numbers. So to begin, let's review the definition of natural numbers. Natural numbers are, in words, just all the positive integers. So they start at the lowest natural number is 1, 2, 3, 4, and it continues in that pattern forever. We've got the definition that if you've got a natural number that is greater than 1, and the only factors that it has is itself and 1, then we would call that natural number a prime number. Okay, so to be a prime number, you first have to be greater than 1, and then the other category is that the only factors that exist for that number are itself and 1. So for instance, the smallest prime number is 2, because 2 is definitely greater than 1. And the only integer factors of 2, or natural number factors of 2, are the number 2 itself and 1, because 2 times 1 is 2. The next prime number is 3. And then our next prime number would be 5. Then 7. And there's actually infinitely many prime numbers. And we'll look at a list of them here below. So the prime numbers that are less than 100 are these, and I definitely recommend that you have this written down on your note sheet for chapter 5. It's something that you'll want to reference throughout all of the sections. Now, if you're looking at a natural number that's greater than 1 and it is not prime, so it's greater than 1, it shares that category, but it's not prime, that's because it has more factors than 1 in itself. We would call that a composite number. So a composite number is just any number that's not prime. So for instance, we know the first few prime numbers, 2, 3, we see that what's missing here is 4, so 4 is a composite number, as is 6, and we could list many such, 100, 200, anything that has factors other than just itself and 1. We know, for instance, 6 has the factors 2 and 3. So all natural numbers can be broken down into two categories. If you're a natural number, you are either prime or you're composite. And these two categories don't share anything in common because by definition, composite numbers are not prime numbers. Okay. Here's a list of the prime numbers less than 100. In this example, we are asked to find all of the natural number factors of each of these numbers. And we know if the only factors are the number itself and 1, we would call it a prime number. If there are other factors other than those two for the number, it would be composite. Let's look at our first example of 7. Now, if there are natural number factors of 7, they will be between the number 1, the smallest natural number, and they could be any number between 1 possibly and 7. So you know the number itself is a bookend, and the way you would think about it is just think through your multiplication facts. What natural numbers multiplied by another natural number would equal 7? We know that's just 1 in itself, but another way you could check this is you could take the number that you're looking at, 7, and divide it gradually by all the integers between 1 and itself. So 1 divides 7 evenly, so 1 is a factor of 7. 7 divided by 2. That's not even, so 2 is not a factor of 7. 7 divided by 3, not a factor. 7 divided by 4, not a factor. 7 divided by 5, 7 divided by 6, finally 7 divided by itself, and that works out. So the only two factors of 7 are 1 and 7, so 1 and the number itself, which tells us 7 is a prime number. Now we'll look at finding all the natural number factors of 35. We know all the factors of 35 will exist between 1 and 35. And thinking through our multiplication facts, we could recall that 5 times 7 is 35. So those are two factors of 35. We also know 35 can be divided by 1. So all of the natural number factors for 35 are 1, 5, 7, and 35. Listed in order, and if you wanted to verify that these are the only 4 factors of 35, though it would be time consuming, you could complete the similar process as before. 35 divided by 1, anything that results in an integer means that was a factor. 35 divided by 2, not a factor. not a factor. And you could just keep doing this with your calculator. And remember, everything that you divide 35 by that gives an integer result. That means 5 is a factor. So this would be somewhat time consuming, but it is a way that you can verify that you're not missing any of the factors if you wish. We're going to continue the same example, asking to find all the natural number factors of each of the numbers given. We start with 44, and then we're asked to find the natural number factors of 88 next. Now, to find all the natural number factors of 44, you could just carefully go through all your multiplication tables and write them down. Another way is I'm going to introduce the idea of a factor tree that we're going to see also later when we find prime factorizations. So with the factor tree, you start with the number in question. For instance, we know that 1 divides 44, so I'm just going to list that out here. And then 44 is an even number. Every even number can be divided by 2. So I'll, with my calculator, say 44 divided by 2. That's 22, so the factors are 2 and 22. So each factor I'm branching out, so think of this branch as saying here, 2 times 22 is 44. And what you should do is whenever you're dealing with the branches, if you ever branch out and you get for instance here, a prime number, that tells you that this branch is done. We're not going to split apart 2 any further. Now we're also not going to split apart 1. 1 is not a prime number, but it's just one of the simplest ones. But 22 is a composite number. It's still divisible, so we're going to keep branching that out. It's an even number, so I'm just going to divide it by 2 again. We know that's 11, or we could just verify with our calculator. We then refer to our list of prime numbers less than 100, and both 2 and 11 are prime numbers. So we know that there's no more work to be done. These are all of the prime factors. So there's nothing more to separate in the tree. And to find all the natural number factors, we then need to work just a little bit more. So first, we always write down 1, 44. The natural number factors will always be the number 1 and the number itself. And then we've got to fill in everything in between. So what I would recommend first is after you've written the first and the second, to verify that you're getting all of it together, we would see that you would look at all of the prime number factors. So 2, 11, kind of where we ended the branch. That means 2 is a prime number, a natural number factor. 11 is a natural number factor. And then there's more. Any intermediate step, for instance, 22 and 44, those are also natural number factors. And you can always verify 44 can be divided by 22 exactly 2 times. So we'd also need to include the number 22. So even though it's not a prime number, it's in the list. Now this is not all the numbers, so we've covered those, we've written down those ones next. The next step is any of the prime factors, for instance 2, 2, and 11, you've also got to include all possible multiples of those prime factors. So 2 times 2, these first 2 prime factors multiplied together is 4. So that means 4 is a natural number factor, and you can verify that 44 divided by 4 divides evenly. Another prime factor to consider is if we took, so here we had taken 2 and 2. Another one is what if we take this 2 and this 11? 2 times 11, we're just figuring out all the ways we can combine the prime factors. That's 22, which we've already included in our list, no need to include it again. The only other possibility of multiplying all the prime factors, we've already multiplied the pairs, is finally to multiply all 3 together, 2 times 11. Which would give us 44, which in our problem we've already included as one of the natural number factors. So our list is 1, 2, 4, 11, 22, and 44. So in the past few examples, I've just been illustrating a few different ways that you could go about this problem. This last method involves making a factor tree of all of the factors, writing down all the prime numbers that you see separately. So for us, we did 2 and 11. Then writing down all the intermediate steps, so that included writing down 44 and 22. And then identifying the prime factors and multiplying them together piece by piece and see what numbers come up. Any new number that came up, we would then want to add to our list because that's also a factor. So I recommend that you would just identify which method you think clicks most with you. And if you do have questions about this, feel free to send me a Canvas message and I'd be happy to clarify further based on your preference. So if you can, pause the video now and attempt finding all the natural number factors of 88 on your own, and then unpause to check your work. In terms of the different methods, you're welcome to choose whichever clicks most with you. Whenever you unpause, I'll be doing the factor tree method. So if you could pause now and then unpause to check your work. So we know 1 is a factor of 88 and it just divides itself 88 times. 88 is an even number. Even numbers are always divisible by 2. 88 divided by 2 is 44. 44 is an even number. It can be divided by 2 exactly 22 times. 22 is an even number. It can be divided 11 times. And the reason I know that I'm not separating these or making these any further trees is all of these at the end are prime numbers from our list of prime numbers under 100. And at that point, you stop. There's nothing else to add in the tree. So let's list out. We first see that we've got 1 is a natural number factor of 88. 8 is a natural number factor of 88. And then we can list all of the prime numbers that we found, 2, and 11. We're not including the repeat yet, maybe 11 somewhere near here. Then we include all the other natural numbers that are factors. They're not necessarily prime factors, but we see 22, 44, we already accounted for 88. So I might have 22, 44. And then this is the point where the only remaining factors are possible multiples of your prime numbers. So our prime numbers are 3 2s and an 11. So we've got to think about all the possible multiples of these. And if they're already included, we don't need to write them down. So first I might just start 2 times 2 is 4. We look at our list, 4 is not included, so that will be added here. Next, we might say 2 times 2 times 2. That is 8, which we look is not yet on our list, so we'll add that too. Now, we haven't dealt with the 11 yet, so for instance, 2 times 11 is 22. That's already included in our list. 11 times 2 times 2. And all of this you can just check in your head as well, is 44, already included on the list. And then finally, if we did 2 times 2 times 2 times 11, that would be 88, which is also already on our list. So in this case, we can verify that these are all our natural number factors of 88. Another neat thing that you might notice is, for instance, 8 times 11 is 88. These natural number factors come in pairs. 4 times 22 is 88. 2 times 44 is 88. 1 times 88 is 88. So that can be another way that you can check your work. You should see these pairs between the factors. For instance, if 11 was missing, I would know it was missing because 8 times what is 11? That would be 88. Okay. These divisibility rules are another thing that you'd want to make sure you include on your note sheet for Chapter 5 material. So I would either print this and then cut it out and tape it to your note sheet, or copy it down by hand. And what it does is it allows you to understand when a certain number is divisible by either the digit 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, and generally a much faster computational way than just trying to do the division in your head or long division. Now, whenever we have calculators, this might not seem as useful because you could just type it into your calculator and check. But for the purpose of this class, let's just pretend that we weren't using calculators at this point, and then we can see how useful this is. In this first example, we're asked to decide whether 1875 is divisible by 5, and then if it is, state the correct reasoning based on the divisibility rules here. So let's first look at the digit 5. I'll highlight it. It says a number is divisible by 5 if the last digit in the number is 0 or 5. So our number was 1875. Looking at the last digit, is it indeed 5? So that fits the criteria. Since the last digit is 5 in 1875, we know by divisibility rules that 1875 is divisible by 5. Okay, let's look at our next example. We're asked to determine whether 156 is divisible by 12. So looking at our list, the divisibility rules for 12 is that if the number itself is divisible by 3 and 4, and I do want to highlight the idea of and, so we only know it's divisible by 12 if we answer the question, is it divisible by 3? And then we also have to ask ourselves, is 156 divisible by 4? If the answer to both of these is yes, then we know that 156 would be divisible by 12. So let's investigate these one at a time. To see if 156 is divisible by 3, we would go to our list. Now 3 says that a number is divisible by 3 if the sum of the digits is divisible by 3. So when it says the sum of the digits, it means look at the number you were given, in this case 156, and add all the digits that make up the number together. So we're not paying attention at all to place value here. We're just treating 156 to add the sum of the digits. It's adding the 1, adding the 5, adding the 6, irregardless of place value. And that would be 12. And then normally when you sum up the digits, that's going to make it a smaller number. It's a lot easier to think about if 3 divides 12 than if 3 divides 156. We actually know 3 does divide 12. 3 times 4 is 12. So we would say, is 156 divisible by 12? Or sorry, by 3? Yes. Next we check, is it divisible by 4? So for 4 we had that if the last 2 digits is divisible by 4, then the number is divisible by 4. And what they mean by the last 2 digits is you look at the number given, 156, and then you look at the last 2 digits and you kind of pull that outside of the number and you think about only them by themselves, the number 56. So notice I did take the last 2 digits of 156 and I ask, is this divisible by 4? And that's just going to make the number smaller. Okay, and then we could even check using our long division. Okay, so it is divisible because we get down to a 0 remainder. You could also check here, 56 is divisible by 4. So 156 is divisible by 4 for that reason. So our answer to this is yes. And then finally, we were asked about, is 156 divisible by 12? So I would say our conclusion, since it's divisible by 3 and 4 separately, we know 156 is then divisible by 12 by our divisibility rules. Next, we're asked if 5,600,054,123 is divisible by 9. So let's reference the rules for divisibility by 9. The divisibility rules for 9 is that if the sum of the digits, so we have to add up all the digits, if when you add up all the digits together, the resulting number is divisible by 9, then the original number is divisible by 9. So we will take our number that we were asked to investigate, and based on the divisibility rules for 9, we are going to add up all the digits, verifying in our calculator to get a new number to consider. So we're adding up all the digits together, and we get 26 as our number when we add all the digits. And now, based on the divisibility rule, we need to ask ourselves, is this resulting number, is 26 divisible by 9? And we would just ask ourselves, does 9 evenly go into 26? No, there's no multiplication rule that says that. Remember, 9 times 3 is 27, but 9 does not divide evenly into 26. So for instance, 26 divided by 9, we get a decimal answer. So the answer to this question is no. And since whenever you add up all the digits together and get 26, since that isn't divisible by 9, by our divisibility rules above, that means that the original number is not divisible by 9 either. The next topic we're going to introduce is that of prime factorization. To begin, it will be helpful to know that every natural number can be expressed in only one way as a product of primes. So what we mean by a product of primes is if you find all the prime factors of that number and then you multiply all the prime factors together, that's going to be equal in value of the number. And there's only one way that we could express that equivalently. We're told to remember order of multiplication doesn't matter. So for instance, if I wrote 2 times 3, that's a product of primes that's equal to 6. That's equivalent in meaning to 3 times 2, which is why we would still say there's only one unique way to write 6 as a product of primes, because 2 times 3 is the same as 3 times 2. Now, this unique product of primes is called the prime factorization. So oftentimes in future examples or your homework or quizzes or exams, you're going to be asked to find the prime factorization of a number. And all that means is do a factor tree like we've been doing in previous examples until you get down to only prime numbers. And then all of those prime numbers can be written as the prime factorization. So we've been told that 50 is 5 times 10 and 50 is 2 times 25. However, neither of these is a product of primes because we know that 5 is a prime number, but we can see that 10 is not prime, it's composite. 2 is a prime number, but 25 is not prime. So this doesn't break the rule given above because it said it's unique only if it's a product of prime numbers. It's not unique if you're allowed to have a product of composites. So in order to find this unique product of primes, we were asked to find the prime factorization of 50. So I would start with my tree here. Whenever the number is even, a good idea is maybe to just first divide it by 2, because we know a number that ends in an even number, so 0 is even, is divisible by 2. In your calculator, you could see 50 divided by 2 is 25. Now, any number that ends in 5 is a dead giveaway, 5 or 0, that it's divisible by 5. So I would next say 25 divided by 5, 5 times 5. And then the reason that I don't expand these further is because if we look at our list of the prime numbers less than 100, all of these are prime numbers. And remember, with this factor tree, once you get to a prime number, you stop. You're done with that. So the prime factorization is going to be from your factor tree. You can circle all your prime number endings, so there's nothing else to simplify. So 50 is going to be equal to 2 times 5 times 5. Notice there was 2 factors of 5, so you would repeat it in the prime factorization. And there's a great way you can check your work here. 2 times 5 times 5. We'll know we got the right answer if when we multiply this in the calculator, we get the original number we were looking at. So this is our prime factorization of 50. Next, we're asked to find the prime factorization of a slightly larger number, 1460. With these numbers, since unless you have intuition about something is divisible by, for instance, I can see that the last digit is an even number, 0 is even, 0, 2, 4, 6, 8. Those are all even numbers, so I know it's divisible by 2. And in my calculator, I would just take 1460, divide that by 2, that's 730. Now 730 again I know is an even number, so it can be divided by 2. 365. 365 ends in 5. Now again, I don't take these any further because they're already ending in prime numbers. 365 I know since it ends in a 5 can be divided by 5. 365 divided by 5, 73. And here we might want to refer back to our list of prime numbers under 100 that we should have next to us. Notice one of the factors was 73. We look through our list of prime numbers less than 100, and 73 is one of them, so that 73 is a prime number. So I know 2 is prime, I know 5 is prime, and I verified 73 is prime. So every end of the branch that we've been looking in this factor tree ends in a prime number. There's nothing else left to do than to write out the prime factorization is each of these prime numbers multiplied together. So it'd be 2 times 2 times 5 times 73. Another way you might see that written is 2 times 2 times 5 times 73. And you can check your work. You would just multiply what you wrote down together. And indeed, that is 1460. So we know that is the unique prime factorization for this number. And I recommend that you write your prime factorization in order from least primes up to greatest primes, just for a nice orderly description. Now this is our last example from this note section. It asks you to find the prime factorization of 285. I recommend you take a moment to pause the video and attempt this on your own, unpause to check your work. Now 285 ends in a 5, so that's a nice giveaway that it's divisible by 5. And that would be 57. Now maybe you were thinking 57 is prime, you weren't sure. In that case, you should look back at your list of prime numbers less than 100 and see that 57 is not on the list. So 57 is composite, so we need to think about what are some divisors of 57. And I just checked first if 57 was divided by 3. It was. The number is 19. So we've got 3 and 19. Now both 3 and 19 are prime numbers, so we've now reached the part of the prime factorization where each end of the branches are all prime numbers. So the prime factorization of 285 is 3 times 5 times 19. And then we just quickly verify that. 3 times 5 times 19 does give us 285. So we can be confident, since these are all prime numbers getting multiplied together that equal 285, this is indeed the prime factorization.